Assalamualaikum. Hi, my name is Nurdana binti Zabah, metric number B0920102773. We from Group 5 will present our assignment, which is automatic electric iron. Introduction. The second order system is unique in this context because its characteristic equation make complex conjugate roots. Second order system with potential oscillatory responses require two different and independent type of energy storage, such as the inductor and the capacitor in RLC filters or a spring and inert mass. Behavior of second order system. This is second order system with transfer function, and GS means transfer function, and this is the equation. This normalized switch characteristic are of a second order gadget without zeros. The step responses of structure are proven in figure 1. And the determination suggests that the parameter omega essentially provide a time scale. The reaction is faster than omega is larger. The form of the reaction is determined by zeta. And control of second order system is control of structure whose dynamic will regarding be outlined via means of differential equation of ordinal order. Such an approximation is affordable in the garage of mass. Momentum and power is also captured via way of mean of country variable.
Assalamualaikum and a very good evening to people who's watching this. My name is Nashin Kisya binti Nazaruddin and my matrix number is B09201035 and I'm from the class BMMP234343. So today I'll be presenting the block diagram, second order system and the model system for the automatic electric iron. So as you can see in the block diagram for the automatic electric iron, we have the thermostat as the input, and then we proceed to the heating element, and the output is sole plate of iron, while the feedback goes back to the thermostat. For the second order system, we simplify it to as it is. We have thermostat, heating element, and sole plate of iron. Next, I'll be showing about the model system. As you can see, the model system is cut off, and it's only as it is, and it's the transfer function. The transfer function for the automatic electric iron, the formula is theta s over delta s equal to cs over rs, and then we will get theta s equals to theta s over delta s equals to 0.6 with multiply with 0.6 multiply with s plus 0.4 over s will multiply with 0.2 and plus 5s plus 15s. That's all from me. Thank you. I'll be passing to my next presenter. Thank you.
Hi, my name is Natira Najwa and I'll be continuing the presentation about calculation and simulation. For the calculation, first of all, we need to find the damping ratio and natural frequency. For these two value, we can find by comparing the value that we get from the block diagram to the general second order transfer function, and then we will get our damping ratio is equal to 0.645 and our natural frequency is equal to 15. After that, we need to find the peak time. The peak time is equal to CP equal to pi over natural frequency square root of 1 minus damping ratio square root of 2, and then we get our peak time is equal to 1.06 seconds. After that, we need to find our setting time. For our setting time, we'll be using the formula Ts equal to 4 over damping ratio times natural frequency, and we will get our setting time is equal to 1.6 seconds. After that, for our percent overshoot, we'll be using the formula as shown, and we get our percent overshoot is equal to 7.05%. After that, for our simulation, I using two kind of application, that is Scilab and MATLAB. For Scilab, we're using the C-scope, CLR, and C-clock, and step function. And for the MATLAB, we shown to show you the graph accurately. For the graph, we need to find the step response of our automatic electric iron. That is the product that we are using to create this assignment. And then first of all, for our MATLAB simulation, we need to insert tab input at common window to get the system response from using common data and correct data and common. For first of all, we use h is the common h equal to tf, and we insert the value that is 1, 1, 5, and 15, and then we use the common step plot h. After that, we press enter, and the graph will be shown. It takes a while. Okay, the graph is shown, and after that, after the graph, which show, we need to find the peak time and the setting time. Okay, how? We can use this. We just right click and choose peak time and peak response and timing, setting timing, and then we can the graph will plotted where is the value. Okay. Okay, there is the value. We can know the value by clicking on the dot, and then show the value. Okay, other than this method, looking the value from the plotted graph, we can also use command. Okay, we can just type the command here. We just type that data is equal to step info h. Step info h, enter, and all this data will show, and this is all the data that given that we can get from the graph. Okay, that's all from me. Thank you.
This table shows the comparison between the calculation value and the simulation value that have been taken from the output graph. For the peak time, TP, the calculation value produces a number of 1.06 seconds, meanwhile the simulation value is 1.07 seconds. As for the settling time, the calculation value is 1.6 seconds, meanwhile the simulation value is 1.55 seconds. As for the percent overshoot, the calculation value is 7.05% and the simulation value is 7.03%. All of the value shows a small gap. The calculation is to convert from system transfer function to state space representation. From the block diagram, we'll get 0.6 open bracket s plus 0.4 over s open bracket s squared plus 5s plus 15. When we multiply in the numbers, we'll get 0.6s plus 0.24 over s cubed plus 5s squared plus 15. Then we separate the numerator and denominator as shown in the figure. Then we'll put in the GS equation, which is CS over RS. Then the value will cross multiply, and then we will differentiate the equation, which produces d cubed x over dt plus 5d squared x over dt plus 15 dx over dt equal to r. The x will then equal to x1, x2 and x3, where x1 is dx over dt, x2 is d square x over dt, and x3 is d cube x over dt. Then we'll put in the equation u equal to r, where x1 dot is d square x over dt, which is x2. x2 dot is equal to d cube x over dt, which is x3, and x3 dot is d to the power of 4x over dt, which is u minus 5x3 minus 15x2. Then we'll put in the numbers into matrix form as shown in the figure. Then the output is Cs over Xs equal to 0.6s plus 0.24. The equation will then be cross multiplied and differentiated, and it will produce 0.6x2 plus 0.24x1. Then we'll put in the equation y equal to c, and it will produce a matrix 1 times 2 of 0.24 and 0.6 times 2 times 1 matrix for x1 and x2.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Atika Binti Zakaria. I will continue the presentation for stability of the system. The stability of the system is ability of any system to provide a bounded output when a bounded input is applied to it. We can state the stability alone. The system to reach the steady state element that state for the particular input even after variation of parameter of the system. If the steady state response consists only of force response, the output of the system can be controlled. For this system, we use the function as 1 over s power the power of 2 plus 5s plus 15. The graph that we obtain from the pole at the origin at minus negative 1 plus minus 2 on the left half plane RHP. Hence, the system is stable. For the calculation, steady state error for that input, random input and parabolic input, we use each step that the calculation we get 0.937. For the ERAM, we get 1 over 0. So we can conclude is equal to infinity, and then E parabolic we get 1 over 0, and E the same for ERAM equal to the infinity. Okay, for the analysis, from the result, we know that the automatic electric iron system in the feedback signal to generate output is a closed loop control system. The electric control system is a system that is able to control the heating and cooling process system when we use the electric iron. We also able to produce the plot diagram for the automatic electric iron control system. In the plot diagram, our input is the heating that user prefer. In terms of enable the temperature change, the control system utilizes a remote control with a thermostat to the heating element and transfer to the sole plate of the iron instrument as a process of the overall system. The basic in working performance by automatic electric iron is such that when the temperature of the sole plate attain a predefined value, the heating action gets stopped automatically. When the temperature fall below at a certain specified value, the automatic electric iron heating start inside it. So we found that in electric iron, the thermostat is provided with a certain specific value, which acts as a reference input of the system. For the conclusion, we have learned that the combination of block diagram and the transfer function is the way we can know the relationship between the output signal of the control system and the input signal for possible input value. The transfer function of a control system is to define the ratio of the Laplace transform of the output variable to Laplace transform of the input variable, assuming in initial to be condition to be 0. In this assignment, we use the automated electric iron as the temperature control system that consists of a thermostat that acts as a controller of the system resistive heating element that represent generate heat. As the system is a closed loop system, a sensor is used to measure of the process variables and get the feedback to the thermostat in the control system. We use the MATLAB software, Skylab software, and manual calculation to obtain the system response. And we can conclude that the control system in automatic electric iron is considerably stable.